Here's the part where I think it gets really cool. So I'd like to think about quad trees as a way of taking our original space and partitioning it. That is, each node, right? So for example, A, it owns 4 subspaces. It has a top left subspace, a top right subspace, bottom left, and a bottom right. And in A's case, that's the entire universe. It's the boss of everything, okay? So if you want to find any data, you have to go through A. But then it also has some subordinates or vassals. So if we look here at B, B is the northeast subordinate of A, and it controls 4 subspaces. It has this one, it has this big subspace, and this subspace. So it's not the whole universe this time. And it, of course, has its own subordinates. And eventually, as you work your way down and down and down the hierarchy, you get to, for example, D, which controls 4 little subspaces here, right? And so if you want to look at any data in these 4 boxes, you have to get through D to get it, okay? And what's neat about this is that the way that the space is divided up is that it's more finely divided in regions where there's more points. Up here to the top left of A where there's nothing, well, there's no subdivisions at all. But over here where there's lots of data, the space is finely divided relatively. And what we'll see is that for common spatial operations like 2D range finding or nearest or other things we haven't discussed, the runtime is often better than you would get out of just a plain old boring implementation of like iterating over all of the data. Okay. Now, let's see how this is so powerful when it comes to doing that rectangle search. And the simple idea is that we're going to prune, that is, not explore subspaces that don't intersect the query rectangle. And here when I say the query rectangle, I mean the green box. Someone wants to know what's in this region of space. So maybe we're using some application where we're actually literally thinking about the sky. And we say, what are all of the stars in this box? This is a data structure you could use to efficiently support that question. So let's see a little demo of how this would work. All right. So if we want to find everything in that green rectangle, we're going to start at the root, which is A. Remember that all data is ultimately controlled by A. You have to get through A to find anything. So we ask ourselves, does A itself intersect the rectangle? No, it's not in the box, so we're not going to include it in our results. Now, we need to make some decisions about what to do next. So there's 4 different subspaces of A. And we know that there's no way that the northwest, southeast, or southwest links could possibly contain any data in this rectangle because these 3 spaces do not intersect that rectangle. So which subspaces might have good points? Only the northeast subspace. And so what we've done now is pruned 3/4 of the infinite universe. That's pretty good. So now we get to B. We ask ourselves, is B in the box? Yes, actually, B is a point which is in the box, so that will be included in our results. Okay. Now we ask ourselves, which subspaces of B might have good points? Now, this is a bit of a tricky question. Try and think about what you think the answer is. Okay, turns out all 4. Any of those points could have, any of those subspaces could contain good results. Why? Well, because the green box intersects this top left, top right, bottom left, and bottom right spaces. So we have to look at all of them, no pruning. So first we look in the top left and we say, oh, well, that's a null link, right? This one right here, the northwest link, it's null, so we just return, nothing to do. Then we look at the northeast link, nothing to do. Then we look at the southeast link, oh, nothing to do. And now we get to the southwest link and we look at C. So question for you, is C in the box? No. So we're not going to include it in our results of points that are in the box. But hey, maybe one of C's children could be in the box. We don't know. So question now. Which of C's subspaces could potentially have good points? Top left, bottom right, top right. What do you think? In this case, only the top right. We know that northeast is the only possible answer, and we can prune the others because this does not intersect, or all 3 of these do not intersect the query rectangle. We only need to look at the top right. So we prune 1, 2, 3 more branches. Now remember, this is my silly little toy example where there's not much data. But there could be, again, many millions of points down here. But because of the miracle of pruning, we would never have to actually analyze them at all. So finally, we would look at this last null link, and at that point, we're totally done. And so what we've done now is we've been able to efficiently support the range search operation. Okay. Now this is a really simple in some ways idea, but also very profound and does give you great results. So for the example below, just to summarize, is that we were able, using the structure of our data structure, it's a little redundant, the nature of a quad tree, to prune lots of the tree. So we never even had to look at any of this data on anything below any of these dotted lines. So again, if there were billions, trillions of nodes to the northwest of A, for example, or to the northwest of C, we just wouldn't have to look at them. Okay? So quad trees are really efficient for this kind of operation.